In class, we started example problem 2, but we didn't get a chance to finish it. For example problem 2, we wanted to find an integrating factor for and solve the given equation. And we determined that it wasn't exact, and we knew we were going to have to use the method of nonlinear integrating factor. So this is the work we had done in class. We got far enough to say, indeed, our given equation is not exact. We know that we can use either the p of x, which is m sub y, the partial derivative of m with respect to y, minus n sub x, the partial derivative of n with respect to x, all divided by n, is p of x. Or we can use q of y, which is n sub x, the partial of n with respect to x, minus m sub y, which is the partial derivative of m with respect to y, all over m. And in this case, I notice that m is only 2xy cubed, and that finding this difference n sub x minus m sub y would yield only one term, so I decided to try q of y. So when we take n sub x, 6xy squared, plus 2xy cubed, and we take away m sub y, 6xy squared, and we divide it by m, 2xy cubed, we find out that we get 2xy cubed over 2xy cubed, which just equals 1. Now to find our nonlinear integrating factor, we're going to use mu of y being the positive or negative e to the integral of q of y dy. So in this case, we would have plus or minus e to the integral of 1 dy. And the integral of 1 dy is just y. So we have an integrating factor of plus or minus e to the y. And I'm going to say choose the positive again. I always choose the positive. So this is where we ended. So what we need to do is we need to finish this problem. So I'm going to scroll up a little bit here and we're going to finish this problem. And my purples may not match exactly, but it'll be close. So let's multiply the entire differential equation by mu sub y. So we want mu of y, oh, I said mu sub y, I meant mu of y. So mu of y times m of xy plus mu of y times n of xy. And it needs to equal 0. And remember, this is now our new f sub x, and this is now our new f sub y. So what we want to do is we want to see, okay, what does this look like now? Well, I now have e to the y times 2x y cubed dx plus e to the y times 3x squared y squared plus x squared y cubed plus 1 dy, and it equals 0. So if I look at this and I see that my new f sub x, which is this side, and here's my new f sub y. If I have to do some partial integration, it sure looks like the f sub x, the partial of f with respect to x, is going to be a lot quicker. So let's try that. Let's do f sub x is equal to 2x y cubed e to the y. And now I need to integrate this with respect to x. So f of xy here would be, well, anything that's not an x is going to be considered a constant, so I can move the y cubed e to the y to the outside, and on this integral I'll have 2x dx. And the way or the reasoning behind why I left the 2 in there is that the integral of 2x is just x squared. So I have y cubed e to the y times x squared plus some unknown function phi of y. that could have been there because its partial derivative with respect to x would have been 0. It's like our constant. So we end up having x squared y cubed e to the y plus phi of y is now equal to our f of xy. So we're looking here. What we also know then is that now I have found f after doing a partial integration with respect to x. Now I need to take a partial derivative with respect to y, and it better equal my f sub y, that is mu of y times n. So let's take a partial derivative of our new f of xy. Well, if we rewrite our f of xy just to equal the highlighted portion, we have f of xy is x squared y cubed e to the y plus phi of y. And if we want to integrate this, differentiate this with respect to y, because we've already started with the partial with respect to x, now we need to do a partial with respect to y, we find that we're going to have to use the product rule. We're going to have to consider this is the first and just e to the y is the second. So if we do that, we say the first, which is x squared y cubed, times the derivative of the second, so the derivative of e to the y with respect to y would be e to the y, plus the second, e to the y, times the derivative of the first. Now remember, we're talking the partial derivative of x squared y cubed, so the x squared is considered a constant, and the y cubed would become 3y squared. And then the partial of phi with respect to y would be phi prime of y. So what we end up having for f sub y is x squared y cubed e to the y plus 3x squared y squared e to the y plus phi prime of y. And we already know from previous examples from section 2.5 and from this section, we know that this also has to equal mu of y times n of xy, which is our f sub y. Let me move it over a little so I can write that in. There we go. So we know that our f sub y then would be e to the y times 3x squared y squared plus x squared y cubed plus 1. And we know it needs to equal x squared y cubed e to the y plus 3x squared y squared e to the y plus phi prime of y. If we do a little simplifying here on the left, we find that we have 3x squared y squared e to the y plus x squared y cubed e to the y plus e to the y. And on the right-hand side, it equals x squared y cubed e to the y plus 3x squared y squared e to the y plus phi prime of y. And we can say, oh, these terms cancel and these terms cancel. So the only thing I'm left with here is that e to the y equals phi prime of y. And I hope that it's fairly obvious then if we differentiate both sides that phi of y is simply e to the y. And remember, we have an implied plus c, but we're letting that constant be 0. So now we can go all the way back to our f of xy and say, okay, it equals x squared y cubed e to the y plus phi of y, which is e to the y. And our last step is that we need to make it equal to c. So we said f of xy equal to c. So we end up with x squared y cubed e to the y plus e to the y equals C. And there is no way to separate out the y's here, so we will leave it in this manner. So we'll leave it as an implicit solution. For our example 3 from section 2.6, we're going to have to use a different method than we use for examples 1 and 2, because we're going to find that when we try to find our nonlinear integrating factor as only a function of y or only a function of x, we can't. Both are dependent on both x and y. So we have to come up with another approach to see if we can make this non-exact equation exact. So let's start by looking at m and n to determine, or in this case to confirm, that they're not exact. So m sub y, which is the partial derivative of m with respect to y, would be 3x plus 12y. And n sub x, or our partial derivative of n with respect to x, would be 4x plus 9y. So what we find out here is that m sub y does not equal n sub x. Therefore, our equation is not exact. Our ODE is not exact. So let's try finding p of x, which is m sub y minus n sub x over n, or let's find q of y, which is n sub x minus m sub y all over m. Let's see what happens when we try to find each one. So for p of x, we would have 3x plus 12y minus the quantity 4x plus 9y all over n, which is 2x squared plus 9xy. So what happens is we get 3x plus 12y minus 4x minus 9y all over 2x squared plus 9xy. So we get negative x plus 3y over 2x squared plus 9xy. We can't use q of x. It's supposed to only be in terms of x and be independent of y, but it's not. So let's try q of y. Maybe we'll have more luck with that one. N sub x is 4x plus 9y, and we subtract from it m sub y, which is 3x plus 12y. And we divide it by m, which is 3xy plus 6y squared. So we end up with 4x plus 9y minus 3x and minus 12y all over 3xy plus 6y squared. Or we end up with x minus 3y over 3xy plus 6y squared. And if we tried to factor out a y or even a 3y, we would still have x minus 2y. So it's still, even if we tried to factor it, it's not going to work. So p of x is not independent of x, or sorry, independent of y. And q of y is not independent of x. So we can't use either one. We can't apply theorem 2.6.1. So we have to come up with a different alternative. And that alternative is pretty ingenious. If you follow a more general argument, so if you're following, right, by following a more general argument that led to the theorem, right, that led to theorem 2.6.1, we want to find functions, right? We want to find functions p of x and q of y, which we just said we couldn't, but let's keep that in mind. We're going to change it a little bit, such that m sub y minus n sub x now is equal to p of x times n minus q of y times m. We know what m sub y minus n sub x is, we know what n is, and we know what m is. So what we're going to do is find that we have a system of equations, and we're going to solve it to figure out what p of x and q of y equal. If you want to know where this concept comes from, I would suggest looking in the textbook to read up on the derivation of how we got to theorem 2.6.1. Unfortunately, there's just not enough time for me to go through all of that. But if we go through now our new version and we start plugging in some of these values that we know, m sub y minus n sub x, we already said was negative x plus 3y, and it equals, and I'm going to abbreviate p of x as just p, times n, which is 2x squared, plus 9xy. And then we're going to subtract from that q of y, I'm going to abbreviate with just q, times m of xy, which is 3xy, plus 6y squared. So what we're going to find is we can simplify this a little bit here. We can say negative x plus 3y equals 2x squared p plus 9xyp minus 3xyq minus 6y squared q. So I'm going to take you on another journey here with substitution, because we're going to simplify a lot of this down to get rid of all of these squares by saying, let's let capital A equal x times p and capital B equal y times q. If we make this simple substitution, we now have negative x plus 3y equaling 2xa, right? And plus 9ya minus, now we're going to be looking at b's. We've got a y and a q together, so this would be 3xb and minus 6yb. So what we can do here is something that's very similar to what we do when we're solving partial fraction expansion. We can look at it and say, okay, I've got x's and y's on the left. Let's see if we can simplify everything on the right to just coefficients of an x term and coefficient of a y term, which we can. We can say, okay, if I pull out an x, I have a 2a minus 3b. And if I add to that pulling out a y, I have 9a minus 6b. And then what we're going to do is, like I said, much like we do in partial fraction expansion, we're going to set the coefficients of the x's equal to each other and the coefficients of the y's equal to each other. So let's do that. So if we look at x's, we have negative 1 equals 2a minus 3b. If we look at y's, we have 3 equaling 9a minus 6b. The beautiful thing here then is we can now use the method of elimination to solve for either a or for b. I chose to eliminate b by multiplying the first equation, the x equation, by negative 2 and leaving the second equation alone. So when we do that, we end up with 2 equaling negative 4a plus 6b for the first equation. Second equation remains the same, 3 equals 9a minus 6b. And when we add it up, we find out our b's canceled, which is what I was looking for, and we have 5a equals 5, so a has to equal 1. Well, now that I know that a equals 1, I can now plug this into any of the other equations to solve for b. So I could say 3 equals 9 times 1 minus 6b, or 6b equals 6, so b equals 1. So a equals 1 and b equals 1. What that tells us then, oops, I started to move some of the writing instead of the background. There we go. So what it means is then that we let A equal XP and we let B equal YQ. So what that tells us is that 1 equals XP and 1 equals YQ, or that P of X equals 1 over X and Q of Y equals 1 over Y. But how does that help us? Well, here's the thing. Now we have an equation for P of X and we have an equation for Q of Y that we can then substitute into those nonlinear integrating factors that we talked about before. We have found a way to solve for P of X and Q of Y. And you might ask, but why do I need both? Before we only needed one. Well, now because our P of X and Q of Y originally were not independent of the other variable, we now have to come up with another way to find an integrating factor that will work. And in this case, what we're going to do is we're going to find a nonlinear integrating factor by saying, okay, I'm going to take our new mu and make it a function of x and y by saying I'm going to multiply mu of x times mu of y. So if we know that our P of x is equal to 1 over x and our Q of y is the 1 over y, we can say here that mu of x would be plus or minus e to the integral of 1 over x dx, which would be e to the natural log of absolute value of x, which would just give us x. We also know that mu of y would be in the same fashion, plus or minus e to the integral of 1 over y dy, which will give us e to the natural log of the absolute value of y, which will, oops, plus or minus there, almost forgot it, which will, oh, forgot those guys, on all of those, there we go, which will give us plus or minus, oops, not e to the, but it'll just give us plus or minus y. So what I'm going to do here is on both of those, I'm going to choose positive x and I'm going to choose positive y. And now our new integrating factor, we're going to say mu of x and y. It's going to be a function of both x and y. So that way it can help us eliminate some of the dependency we had before. We're going to say let's instead take that as a product of mu of x times mu of y. Or in our case, x times y. So our new nonlinear integrating factor is xy. So what we're going to do then is to go back and say, okay, so now I'm going to do mu of xy times m of xy dx plus mu of xy times n of xy dy, and it's going to equal 0. So in this case, we're going to have xy times 3xy plus 6y squared dx plus xy times 2x squared plus 9xy dy, and it's going to equal 0. So if we do a little bit of simplifying, we now have 3x squared y squared plus 6xy cubed times dx plus 2x cubed y plus 9x squared y squared times dy, and it equals 0. We have a new f sub x and a new f sub y. So our new f sub x here and our new f sub y here. So I think I'm going to choose to start with f sub x because I think that would be a little easier to integrate. So let's say our f sub x, or our df dx here, is equal to 3x squared y squared plus 6xy cubed. And I want to integrate that to find f of xy with respect to x. So my y squared becomes a constant out front, and I'm going to integrate 3x squared dx. Plus, I'm going to bring my y cubed out to the front because we're treating it like a constant. And on the inside, I'm going to have 6x dx. So if I simplify this, I get y squared times x cubed plus y cubed times 3x squared, and then some phi of y that could have been here. So if we simplify, we end up with x cubed y squared plus 3x squared y cubed plus phi of y. So if we then rewrite our f of xy, now that we've got it all figured out, we've got x cubed y squared plus 3x squared y cubed plus phi of y. And now we started with a partial with respect to x and took an integral. Now we need to go back the other direction and take the partial of f with respect to y, which means x cubed is treated like a constant, so y squared would become 2y. So we'll put the 2 out in front of the x cubed, so 2x cubed y. Plus, well, the 3x squared is treated as a constant, so it would be 3 times 3 is 9, and the x squared stays, and the y goes down to a square. And we have phi prime of y. But we also know that this needs to equal 2x cubed y plus 9x squared y squared from above, from this f of y. So if I set them equal, an interesting thing is going to happen. My phi prime of y is going to end up just equal to a constant. So, because, oops, I didn't show you, there you go, because these guys cancel out, these guys cancel out. So I end up with 0 equaling phi prime of y. So phi of y is just going to equal a constant, and as we said before, we're going to let that constant be 0. So after all this work, it turns out we don't really even have a phi prime of y. So if we were to rewrite our f of xy now, we would have f of xy equals x cubed y squared plus 3x squared y cubed. And in the end, we know that we also have to set this equal to a constant. And we will leave it at that because we can't factor out the y's in order to solve and keep the y's separate from the x's. So we will have to leave it as an implicit solution.